Now that we have our basic axioms, 0, 1, and 2, let's actually look at seeing what kind of geometries we can build. And for that, we're going to need the idea of a model. And a model is just a representation of an axiomatic system. So we have our axioms, a model is just some kind of representation of that. And there are a few things that we're going to assume whenever we draw these. The first thing is that dots are going to represent points. Thin lines or arcs are going to be our lines. So our lines may not necessarily be straight, they could be arcs. And finally, the only points on the lines are the dots exhibited. So for this, we're actually not going to consider all of the points in the plane, but just the points that we actually draw. At this point, we've really only had 3 axioms, axioms 0, 1, and 2. And there are lots of different examples of things that satisfy those axioms, but we want the most basic one. So axiom 1 said that a line is a subset. In fact, it said a line was a proper subset. So the minimum I can have is a line and another point. Axiom 1 said that every line had to have at least 2 members, so there needs to be at least 2 points on this line. And then axiom 2 said for every 2 points they have to belong to a line. So I need a line between these 2 points as well as between these 2. My drawing's not quite perfect, but we do get the idea. And this is by far not the only example of something that satisfies these 3 axioms, but it is the most basic example we can have. Let's look at another example, this time one with 4 points. We know that between every 2 points, we need a line, and we know a line needs at minimum 2 points. So I'm actually going to draw this one slightly different. So this arc that I just drew is a single line, and this one down here at the bottom is another single line. So I essentially have 3 lines here. This is not the only way to do one with 4 points, but it does show you just another example. This time my top and my bottom line actually contain 3 points rather than the required 2. Let's do another example. This time I have the points as A, B, C, D, and this is my list of lines that I need to draw. So we want to find a model that satisfies this information right here. So I have 4 points, and we'll label those A, B, C, and D. I know I need a line between A and B, between A and C, and between A and D. My next line is between B and C, and then B and D, and then my final line between C and D. So we now have this intersection at the center. However, it's important to realize that this right here is not a point in my geometry. I should only have 4 points. So intersection of line segments in a model does not necessarily mean there's a point there. And so if we want to model where non-intersecting lines have to be non-intersecting arcs, so not like this, essentially if we want something where every intersection has to be a point, that's known as geometrically faithful. And there's nothing unique about this drawing right here. Here's another model for the exact same geometry that I drew previously. It has the same points and the same lines, but this time it's geometrically faithful because I don't have these intersecting lines that aren't supposed to be intersecting. And even this isn't unique. Here's another example of that exact same geometry, but this time it's still geometrically faithful. And so this is a big problem in geometry, is we want to be able to tell whether 2 models are the same just because they look differently. And so this is one of our big problems. We have 2 models, they look very different. Are they actually the same? Do they have the same points and the same lines? Let's do a couple more examples here. Here's another example. We have 4 points A, B, C, D, and this time we have 4 lines. We don't want to draw this one. Instead, we want to know, is this a geometry? Does it satisfy all three of our axioms? Axiom 0 just said that a line was a proper subset. So in order to do that, we're looking to see if there is a line that passes through all four of my points. And we can see in this list of lines, none of them are defined by all 3 points, or all 4 points. So we do satisfy axiom 0. Axiom 1 said every line had to have at least 2 members, and we can look through this list and see that every line has a minimum of 2 points on it. And then axiom 2 said for every 2 points they belong to a line. So now it's time to start checking things. And we need to look at all possible pairs. And here's all 6 possible pairs of my 4 letters, A, B, C, D. So we can see A and B is satisfied since both L1 and L2 pass through both A and B. L1 passes through AC, and L2 passes through AD. L1 passes through BC, L2 passes through BD, and then finally L4 passes through CD. So yes, this is valid. It does satisfy all 3 of my axioms. So here's all possible combinations of 2 points. We can see line 1 satisfies AB. It also passes through both A and C. Line 4 passes through both A and D, as well as A and E. Line 1 passes through both B and C. Line 2 passes through B and D. However, we now have an issue. There's no line that has both B and E in it. So this actually does not satisfy my axioms and would not be a valid geometry based on those. This one goes a little backwards from what we've been doing. So here's a model, and you can check it does satisfy all 3 of my axioms. So I want to name the points P and then all of the subsets that are lines. So for the points, we can see we have 5, A, B, C, D, and E. I'm then going to take the lines piece by piece. So I'll start with this top one, and we can see that it passes through A, B, and C. The next one going down passes through A, D, and C. The next one down just passes through A and C. The one at the bottom goes through A, E, and C. And then finally, the vertical one passes through B, D, and E. So we now have all of our points and all 5 of our lines.